Hello everyone, today we're going to look at integration. So hopefully you watched the previous video on the idea of the integral. So what we have here is the integral of f of x dx. So remember that this symbol and the dx are one entity. You can think of them as bookends. I have to have both of them, or I can't have either. Okay, so I can't integrate without the integral sign, and I can't integrate without the dx, because this is telling me my variable. And it's very important, especially if you ever take a multivariable calculus class. You can have multiple variables going on, you have to know which one you're integrating with respect to. So our goal here is to find the function that we typically call capital F of x, such that the derivative of capital F equals lowercase f. So we're going backwards. With differentiation, we were given the function, we had to find the derivative. With integration, we know the derivative, we have to find the original function. So let's start with the most basic. What is the integral of dx? So remember that the function here we can think of as a 1. So dx is 1 dx. So we ask ourselves, whose derivative is 1? Hopefully we can agree that that's x. If I take the derivative of x, I get 1. But it's not just x. It can be x plus any constant. X plus 2, x minus 5/3, x plus pi cubed over 7. Right? Because the derivative of a constant is 0, so I can always add a constant, and it's not going to change the derivative. So the integral of dx equals x plus c. All integrals are going to look like some function plus c, because again, I can add any constant that I want to the function, and it's not going to change the derivative. So let's try another one. The integral of x dx, whose derivative is x. So we have to kind of think backwards and say, when I differentiate something, when is it that I get x? So hopefully x squared comes to mind. The derivative of x squared is 2x. So we're really close. We want just 1x. So how do we get rid of that 2? Well, the 2 is being multiplied, so we need to divide by it. So the integral of x dx is 1/2 x squared plus c. And don't forget, you can always check this by differentiating the right-hand side and making sure you get the integrand, which is what's inside the integral. So if I differentiate 1/2 x squared, I do get exactly x. What about the integral of x squared dx, whose derivative is x squared? So again, you have to think backwards. Say, okay, when I differentiate something, when is it that I get x squared? So we have that the derivative of x cubed is 3x squared. So again, just like with the 2, I need to get rid of that 3, so I'll divide by it. So the integral of x squared dx is 1/3 x cubed plus c. And in general, the integral of x to the n dx equals 1 over n plus 1 times x to the n plus 1 plus a constant. This is true as long as n is not -1. So remember, x to the -1 is 1 over x. So this doesn't work for the integral of 1 over x dx. You'll learn that in Calc 2 if you take it. And that's because you would be dividing by 0 here. So before we integrate, let's talk about why it is 1 over n plus 1 times x to the n plus 1. So remember, this is the opposite of differentiation. When I differentiate x to the n, I take the derivative, I multiply by my exponent, and then I subtract 1. So I multiply and then I subtract. To undo that, I have to add, because that's the opposite of subtraction, and I have to divide, because that's the opposite of multiplication. Okay, so remember, you're undoing the derivative, so I have to do everything backwards. So it was multiply, then subtract by 1. So the opposite of that is add 1, divide. Okay, so now let's try some examples. The integral of x to the 5th dx. So again, I need to add 1 to my exponent. So my new exponent is going to be x to the 6th. And then instead of multiplying, I divide. And then I add my constant. Integral of x to the 2/3 dx. Again, I add 1, so 2/3 plus 1 is 5/3. And then remember, I'm going to be dividing by a fraction, but that is multiplying by the reciprocal. So whenever my exponent is a fraction, I want to multiply by the reciprocal and add c. The integral of x to the -2 dx. Add 1 to the exponent. So -2 plus 1 is -2. Dividing by -1 is multiplying by -1 plus c. The integral of x to the 100th dx. Again, I'm going to add 1, so my new power is 101, and then divide by it. So I get 1 over 101 times x to the 101 plus a constant. Just like with differentiation, you can distribute an integration across coefficients and addition, subtraction. So if I have something like the integral of a times f of x plus or minus g of x dx, I can separate it across the addition and subtraction, and I can also move the coefficient out. But I can only move it out if it is in fact a coefficient. So a has to be a number. It can't include a variable. So this means we can integrate polynomials. So what is the integral of 3x squared minus 7x dx? Whenever your integrand, again what's inside the integral, is more than one term, you need to have parentheses around it. Because again, the dx and the integral sign are bookends. Everything in between is something, and that has to be in parentheses if it's more than one term. So I'm going to separate it across the subtraction, and I'm also going to take the coefficients out. So it becomes 3 times the integral of x squared dx minus 7 times the integral of x dx. Again, each integral has a dx attached to it. So for x squared, that's going to become 1/3 x cubed, and I still have my original 3. And then minus the 7, and then x, the integral of x dx is 1/2 x squared. Right, we did both of these guys earlier. There's only one constant, so you might think, well, there are two integrals, there should be two constants. But a constant plus a constant is still a constant. Okay, so c is just a constant, it's not something in particular. So all my constants together is still just a constant. And then lastly, I'm going to clean up my multiplication. And this becomes x cubed minus 7/2 x squared plus c. And again, you can always double check it by differentiating. So let's try the integral of the square root of x minus 1/2 square roots of x dx. So the first thing we want to do is rewrite them so that they're in exponential form. So the square root of x becomes x to the 1/2. 1 over the square root of x becomes x to the negative 1/2. That 2 is still in the denominator. I have a lot of people who want to write this as 2x to the negative 1/2. But this is still 1/2. That hasn't changed. And then I pull it out front because again it's a coefficient, so I can. Okay, so just be careful that 2 is still in the denominator. It is still 1/2. It's only the x that gets moved up. And now we'll do the rules of it. So x to the 1/2, I'm going to add 1 to it. So I have 3/2. Dividing by 3/2, again, is multiplying by the reciprocal. So I'm going to multiply by 2/3. And then for my second one, I have the 1/2 from before. And then negative 1/2 plus 1 becomes x to the positive 1/2. Divide by the fraction, multiply by the reciprocal. So dividing by 1/2 is multiplying by 2. And then lastly, I'll clean it up. So we have 2/3 x to the 3/2 minus x to the 1/2 plus c. And again, don't forget, you can always check it by differentiating. And then x minus x squared plus 4x to the negative 4th. What's the integral of that dx? So here I'm not going to physically write it out with the different integral signs, but just remember that we're going to integrate these piece by piece. So x becomes 1/2 x squared minus 1/3 x cubed. Again, I've done those two a couple times now. And then the integral of 4x to the negative 4 dx, add 1 to negative 4 to get negative 3. I still have the 4, and then I'm dividing by my negative 3. So my plus 4x to the negative 4th, when I integrate it, becomes negative 4/3 x to the negative 3, and then adding a constant. What if instead of x to the n, we had u to the n, where u is some function of x? So what we're going to do is we're going to undo the chain rule. Remember, the chain rule is a composition of functions. So something like 2x plus x cubed to the 3rd. I have a function being raised to a power. So again, to differentiate it, we did the chain rule. To integrate it, we're going to do something called u substitution. It starts off very similarly to what we did with differentiation. So I have the integral of x squared plus 1 cubed times 2x dx. So u is the function being raised to a power. So in this case, x squared plus 1. I'm going to differentiate it just like we did with the derivative. So du dx equals 2x, and I'm using Leibniz notation, du over dx. Remember, the top one is my function, the bottom one is my variable. And I'm using this so that I'm going to have my d, my variable, in this guy. Okay, so it's not a coincidence that I'm using Leibniz notation here. The next step is I'm going to treat du over dx as a fraction, and I'm going to multiply both sides by dx. So I get du equals 2x dx. So whenever I'm doing this, everything on the left has to be u, and everything on the right has to be x, or whatever variable we're using. So once I've moved that dx over, everything on the right is x's, everything on the left is u's, and they're never going to cross again. So only u's on the left, only x's on the right. Next, I'm going to look at what I have in my integral besides my u to the function. So in this case, I have 2x dx, and that is exactly what I have over here, which is what I want. So I have 2x dx in my integral, I have 2x dx in my equation with my u's, and that is lovely. That's exactly what I need. So what we're going to do is we're going to substitute into our integral, hence u substitution. And everything with an x in my integral has to go away, and everything that's left has to be in u. So I cannot have u and x's in my integral once I've done the substitution. I can only have u's. So my x squared plus 1 is going to become u, and my 2x dx is going to become du. So I'm left with the integral of u cubed du. So again, my variable has to match here, u and u. And now it's the power rule, so that rule that we just learned. I'm going to add 1 to my exponent, make it u to the 4th. divide by it, add c, and then lastly, plug back in what u is. So 1/4 times x squared plus 1 cubed plus c. Okay, so again, it starts off the same as differentiation. U is my function that's being raised to the power. I differentiate, but now instead of doing u to the n, nu to the n minus 1 times the derivative, there's a little bit of substitution going on, and I'm going to integrate with respect to u. So let's try some more. The integral of 3x cubed times the square root of x to the 4th minus 3 dx. I noticed that I have the square root of a function, so u is going to be that function. So u equals x to the 4th minus 3. Du dx is 4x cubed. And as soon as I get to this point, I want to stop and I want to make sure that I'm doing this correctly. And I do that by looking at my variable. So I can ignore the coefficient. The coefficient doesn't really matter, but it's the variable that's very important. So I have x cubed, and I have, again, not including the u to the power, I also have x cubed. So those have to match. If I had x squared and x cubed, I wouldn't be able to do this. So at this point, I want to make sure I have x cubed, I have x cubed. Good, I'm on the right track. And then, again, I'm going to move that dx over. So I have du equals 4x cubed dx. Next, I'm going to look at the coefficients. So I have a 3 up here, and I have a 4 down here. If one of those numbers is not a multiple of the other, then what I'm going to do is I'm going to divide both sides of my equation by the coefficient that I have. So I'm going to divide both sides by 4 and get rid of the coefficient altogether. So 1/4 du equals x cubed dx. And then I'm going to start looking at my substitution. So I have the square root of x to the 4th minus 3. That's going to become the square root of u. My x cubed dx. Remember, this is multiplication. The order doesn't matter. So the fact that the square root of x to the 4th minus 3 is in the middle there doesn't matter. It's the same thing as x cubed dx. Okay, that's going to become my 1/4, which again, coefficients go out front, du. And then I still have this 3. So I'm going to shove that in there. So I have the 1/4 du, I have the square root of u, and I have the 3. So I'm going to clean this up. My 1/4 times 3 becomes 3/4. Again, that's the coefficient. I'm going to pull it out of my integral. And then I have root u du. So again, the du is always at the end. Okay. So that's what I have. And then in order to integrate it, I am going to change what the square root of u means and make it 3/4 times the integral of u to the 1/2 du. And again, this is something that we integrated earlier. So 1/2 plus 1 becomes 3/2. So that's my new exponent. I have the 3/4 from before. I'm dividing by 3/2, so I'm multiplying by 2/3. So I'm going to clean up my coefficients and replace back what u is. So my 3's cancel, 2/4 is a half, and then again u, x to the 4th minus 3, to the 3/2 plus a constant. Let's try another one. The integral of 1/3 minus 5x cubed dx. U is the function being raised to the power, so 3 minus 5x. When I differentiate, I get -5, and then typically we don't do du dx equals and then move the dx over. We typically just do it in one go. So this is really coming from du dx equals -5. Don't forget that negative. A lot of people will just drop that negative, so that negative is still there. And then move the dx over. So we typically skip this middle step. So du equals -5 dx. And again, in my integral, I have 1 dx. So I want to get rid of that 5, so I'm going to divide by it. And I'm going to get rid of the negative as well. So I'm going to get rid of that negative 5 by dividing by it. So negative 1 over 5 du equals dx. Then I do my substitution. My dx becomes du. Here I have 3 minus 5x cubed in the denominator. So that's 1 over u cubed. And then again, that negative 1/5 I'm going to pull out because it's just a coefficient. I'm going to rewrite 1 over u cubed as u to the negative third so that I can do that power rule. And then I have the negative 1/5. My new power is negative 2. Divide by it, so multiply by negative 1 over 2. Clean it up. I have a double negative, so that becomes positive 1/10. 3 minus 5x to the negative 2 plus a constant. So let's try another one. The integral of 2x squared times 4x cubed minus 9 cubed dx. So again, I have a function being raised to a power. So I'm going to let u be that function. Then I differentiate. Again, I'm going to bring that dx over at the same step. So the derivative is 12x squared. Bring the dx over. So now I'm going to look at my coefficient that I have in my integral, the coefficient that I have in my derivative. I want a 2 and I have a 12. Luckily, 12 happens to be a multiple of 2. So instead of dividing by 12 and getting rid of the entire coefficient, I'm just going to divide by 6 and keep that 2. So 1/6 du equals 2x squared dx. And that is exactly what I want. So that whole thing, what's blocked off in blue, is going to become 1/6 du when I do my substitution. And again, I'm going to pull the 1/6 out, and then I have u cubed du. When I integrate, my u cubed becomes u to the 4th. I multiply by 1 over 4. Still have that 1 over 6. Simplify it, so 1 over 24. Plug back in what u is. So 4x cubed minus 9 to the 4th plus c. And then here's our last one, the integral of the x dx over 4 times the cubed root of 5 plus x squared squared. So it looks a little messy, but again, we're going to just do it step by step. So u is 5 plus x squared, that function that's being raised to the power. I don't include the squared because that's still a power, so it's just the 5 plus x squared. Du is 2x dx. Again, the derivative is 2x. I'm bringing over that dx. I have x dx and 2x dx. I want to get rid of that 2, so I'm going to divide both sides by 2 and get 1/2 du equals x dx. So I'm ignoring that 4 in the denominator for just now, but we'll bring that back in. Okay, so when I start doing my substitution, again, my numerator becomes 1/2 du. Then I have the 4, then I have the cubed root, then I have u squared. I'm going to simplify my 1/2 over 4. Right, that's going to become 1 over 8, and that's going to bring that outside of my integral. And then I still have du over the cubed root of u squared inside the integral. And now I need to, again, rewrite this so that it's a power rule. So remember, the cubed root becomes to the 1 over 3 power. So the cubed root of u squared becomes u to the 2/3. The fact that it's in the denominator means it comes up as a negative. So I have u to the negative 2 over 3, and the integral of that du, and then I still have the 1/8 on the outside. So I'm going to add 1 to my negative 2/3 to get positive 1/3. Dividing by a third is multiplying by 3. So 1/8 times 3 is just 3/8. And then plug back in what u is. So 3/8 times 5 plus x squared to the negative 1/3 plus c. And again, just like the earlier ones, you can always check this by differentiating. You will need the chain rule, but you should be able to differentiate it and get exactly what you started off with. Okay, so make sure that you read through the book, try the homework, and let me know if you have any questions. Thanks.